Go back the other way. How do we then integrate our exponential? Well, if I have e to the power of some linear function, and I'm just talking about linear functions to start off with, if what I did when I differentiated was I multiplied by essentially the coefficient of x, because we differentiated, then to integrate, go back the other way. What's the opposite? It's division. So I'll divide by that coefficient. Okay, it's great if it's a linear function. A lot of times it's not. So it's probably better to think of it with this idea, like we did for some of those other functions, where, hey, if I can get it into the form of something, if I've got my answer in the form the derivative times e to the function, then I know it goes back to just e to the function. So I want to create the derivative out the front. And that's probably an easier way of thinking about it. Although you get something like this, e to the 5x, because it's linear, oh yeah, okay, 1 over 5, it's probably quick, just go, right, yeah, 1 over 5, e to the 5x. Of course, I could have, using that second idea, have gone, oh, what I really would have liked is in the form derivative times e to the function. So I really would have liked 5 times e to the 5x, but I can't change the question. So to balance it out, I'll multiply it by 1/5. Well, I know that the integral here goes back to e to the 5x and I get the same answer. You see what I mean? If it is a linear function, it's probably easier just to go, oh, well, it's 1 over the coefficient of x. It's going to be quicker to think of it that way. But of course, you get something like this, you can't do it that way. And you go, all right, I want to create the derivative out the front. And the derivative is 2x. To balance it out, that's a half. And so I get a half e to the x squared. It goes back the other way. Yeah, integral of e to the 9x minus 5. If I'm doing it in that way of thinking about, I want it to be derivative times the function, then I'd say, well, it's 9 e to the 9x minus 5. Multiply it by 1/9. There's my answer. Ooh, square root of e to the x, got to change it into index form. Again, linear function, I could just go 1 over a half, which is 2, or I could say, hey, I want to create derivative times e to the function, so it'll be a half, balance it out, and of course, they've given it to me in third form, so I like to give my answer the same way. I end up with 2 root e to the x, plus, of course, a constant. Don't forget your constant of integration. Ooh, wouldn't it be nice to have a product rule for integration? Well, we actually kind of do, but not at this level yet. We'll get to that when we look at extension 2 integration. But at this stage, we'd say, hey, we've got to expand the whole thing out. I probably would anyway, to be honest, for something like this. And then integrate each individual part. Quotient rule. Oh no, we don't have a quotient rule for integration. But that's all right, because this fraction will simplify. I could rewrite it as e to the 3x minus e to the minus x. Integrate each term, and we have it 1/3 e to the 3x plus e to the minus x. Plus, of course, a constant. Let's do a definite one. X squared e to the x cubed. So I would like it to be 3x squared. That would have been nice. So multiply it by 1/3, and I now know that that integral goes back to e to the x cubed. Substitute in 1, substitute in 0. Please don't make silly mistakes like e to the power of 0 is not equal to 0. So easy to do. It is, of course, 1, just like anything else to the power of 0. And we end up with 1/3 e minus 1. We didn't talk about that, did we? A base. What do I do? Again, think. When I was differentiating, how did I solve the problem? When the base wasn't e, I multiplied by the natural log. Integration is going back the other way, so it's logical. I'll divide by the natural log of the base, and then I can just do it like anything else. So integral of 3 to the x is just 3 to the power of x, but I'll divide it by the natural log of 3. Okay, there we go.